Welcome everyone to our webcast today. As Ashley stated, I'm Eric Valentino, electromagnetic sim specialist here at RANSIM. My work involves performing simulations for clients and helping clients get the software that they need to succeed. So without further ado, we'll just jump straight in. So the agenda today is going to look like the following. First, we're just going to go over some concepts related to thermal reliability, how it affects your designs, etc. Then we'll get into IcePak and how it can simulate thermal information in basically any design scale. Then we'll have a little blurb about Sherlock and then get into their integration, which is the meat of the presentation. And then after that point, we will open it up for questions. So what is thermal reliability? First, we'll just talk about what reliability is as it pertains to electronics. So the kind of dictionary definition would be that it's the probability that a piece of equipment operating under specified conditions shall perform satisfactorily for a given time period. So long story short, how well your design is going to perform over time. Expanding on that, thermal reliability would be minimizing that probability of failure coming from any cause associated with the improper management of heat. So what kind of things do we need to think about in order to be thermally reliable? So first and foremost, we're going to have to get a good picture of how our design is operating in the nominal conditions. So just whatever temperature you're intending for it to work at, whether or not there's cooling, etc. Getting a good picture of what it looks nominally will be the very important foundation before you jump the gun with any kind of reliability simulation, having not done that first. After which, one can simulate the operation of a device as the ambient temperature around it varies. So exploring whatever series of temperatures is within your rating and simulating the design in those environments. And then lastly, going through thermal cycling, which can cause different issues as we will see in the following slides. So what are our goals for reliability? So you can think of there being three major pillars that are desirable to attain. First, you have your performance, then you have safety and cost, with safety probably being the most important. So safety, of course, you don't want to harm anyone with your design. It's pretty self-explanatory. You want it to be reliable, both for reasons of PR types of reasons and also warranty types of reasons. And then also cost. We want to do the first two, achieve a good performance and proper safety without kind of breaking the bank. So what kind of things happen physically which might fall under the purview of thermal reliability? What's going wrong? A few of the physical effects are going to be covered in the next couple of slides. The first one being cracking and faults due to varying coefficient of thermal expansion. This is a really big one, and it's kind of broad and it affects many different types of things. So the first thing that might come to mind is your solder joint fatigue here. That's illustrated on the right. What you have in this little diagram is 3 different temperatures and then kind of an illustration of the mechanical stress and strain that's going on. So during the normal operating temperature of a device, you may have let's say a package which isn't expanding or contracting. Let's say the package is very consistent as to its coefficient of thermal expansion, but you have a board that has a higher positive coefficient of thermal expansion. When you bring the whole assembly up to a higher temperature, the board is going to expand. The part will stay the same size. This will create a kind of a shear force on the solder. And likewise, vice versa, if you take the whole assembly below this neutral temperature, you'll see a shear force in the other direction across the solder as the PCB shrinks while the package is staying the same size. This little graphic is relevant since this was a big issue for a gaming console, the Xbox 360, causing a very common problem that was well known. After which, another big one is semiconductor degradation. So whenever you have a transistor or a diode with a PN junction, of course, which they all have, whenever you're increasing temperature, that forward voltage is going to decrease. I'm sure you can imagine a couple of scenarios in which that would not be good. So that forward voltage is also what's determining the on voltage for BJTs, a little bit different for FETs. But you can imagine having, if you had taken your design from room temperature to say 150 degrees, one can imagine a scenario in which a transistor which didn't used to be on is now on, and when you are not intending, causing some potentially causing some big issues for design. Another one that's kind of on a smaller scale is electromigration. So electromigration is kind of caused by literally charge carriers bumping into atoms within a conductor lattice along a fault. And as a design gets hotter, those atoms are more likely to move and be bumped by electrons, and that can cause a couple of different modes of failure. On the right, we see an open circuit failure that's caused by this action, and similarly a short circuit failure. If you get enough of these atoms moving out of a fault, you can actually short from one conductor to another. In addition to this, you got good old burning and melting. If your design is at a hotter operating temperature, less thermal power energy is going to be needed to cause a trace to be burnt out. Also melting. Certain packages and maybe standoffs, enclosures come to mind, which can in turn cause electrical failures. Another big one that's kind of more related to the performance rather than a catastrophic failure would be an increase in resistance due to temperature. So that could be in your lines or actual physical resistors themselves. Increases in these resistances could potentially cause your design to become more lossy or just in general bring it away from its operating point. And likewise, excess noise. One can envision maybe a receiver in which operates very well at room temperature, but once the temperature is raised and more thermal noise is introduced into the picture, the receiver could not work properly. So what should we do about this? How should we insulate our design from thermal failures? So a kind of traditional design cycle is as follows. You design your product, build it, test it, break it, figure out what's wrong, and then go back to the drawing board, correct? Obviously, this should be maintained since it's very expensive and labor intensive. And especially in these days where you might be waiting months for a specific part, you don't want to waste all of your processors that you waited a couple of months to get on prototypes that aren't going to work anyways. So it behooves us at this present time to do as much as we can in simulation and minimize this design cycle as much as possible. And we can quantify how simulation can reduce that design cycle action. So using reduced order models, which is something we might talk about after the presentation, we can increase our sim speed and do simulation design cycles at just a fraction of a fraction of a fraction of the speed that you might do the same simulation or the same tests on the bench. You can, in general, reduce your design cycle by 75% of what it used to be. And you can save money on cost for prototypes, which is another cost in addition to labor. And all of these are backed up by various studies, which of course compare the inclusion of simulation in a design cycle to a simulation-free design cycle. So now we're going to get into our simulation solution for thermal in general, what it can do, and kind of touch on that first point that I had concerning simulating our design at its nominal operating region. With IcePak, you can do that for basically any design scale, which we'll see a little bit later. And here we just have a few of the things it can do, which allow one to make a very get a very accurate picture of what's going on with your specific design on whatever scale it's at. So of course, you got fluid flow needed for convection, think cooling fans and stuff like that. Conjugate heat transfer also kind of composes that as well. So yeah, convection, conduction, heat sinks, conduction through your board, through components, radiation. So you got, bigger designs here. This is black body radiation, thermal, or solar. Think like maybe a big dish that the sun is shining directly on. That's gonna heat it up, and IcePak can model that. And also Joule heating. So by Joule heating, it means the heat that's dissipated when current travels through a resistor. So you can do steady state or transient, which we'll show the importance of later. Multiple fluids, so you can have air cooling or water cooling, and model convection in both a cooling circuit and the air around it. You can do optimization in IcePak itself, species transport, reduced order modeling. So this is taking a model and making it simpler. We can get into this more later for the purpose of speeding up your design cycles in simulation, and multiphysics coupling, which we'll expand on over the next couple of slides. So here we got some pretty pictures. We got our a drone here, which IcePak is simulating the CFD around resulting from the spinning propellers of this drone, and how temperature is dissipated as a result. And something a little simpler, we have what looks like is an electronics enclosure with some convection due to a fan and the inclusion of a heat sink. So like we were saying before, our first step to getting a good thermal reliability is just getting a great picture of what our design is going to look like as it's operating under normal conditions. So we're going to optimize our cooling strategy at that point, and really just get a good understanding of what are the heat sources, how we can mitigate them. So we'll do this at many different scales through integration with different Ansys solvers. And we can optimize the performance and dial in the accuracy of our simulations with the reduced order modeling. So at the end of the day, you'll get a design which is going to be cooler and more reliable through this process. So this is a little bit more about all the different scales which IcePak can work on. So we can go from chip design, chip layout, all the way to a big server room or maybe a cell phone base station. So in between those, we have package level. So the level of like inside of a package, laying out bond wires and thermal performance, which would be mostly conduction at that level. PCB, which is a big one, which we have. There's many, lots of tools here. Integrating different PCBs, integrating enclosures, and like I said, the whole room level or system level. So first we'll go into a little bit more about that chip thermal reliability. So we can do this through coupling with Ansys Red-Hawk, which is our die layout tool, which will simulate, of course, the semiconductor performing with your specified geometry. That semiconductor, of course, is temperature dependent, and Red-Hawk can take in temperature information. So what you can do is get a better picture of how your chip would be performing thermally with this design cycle. So you would do your electrical simulation first and export a model, simulate an IcePak, and then get more accurate temperature information here. One design level up is the package. Similarly, they need to be thermally performant. You would like them to radiate heat properly due to joule heating on the die, etc. So this can be done in a similar fashion. And one can even automate JDEC test chamber setups for specific chips. Next is the PCB. This is probably the most often used scale. So similarly to the chip, what we're gonna have is maybe a power simulation, an electrical simulation first of your power distribution network, what kind of currents are in which traces. Once this simulation is performed, that information can be sent to IcePak. The joule heating is modeled, and also along with convection and conduction. And then you get back into your PCB tool, that would be SI wave in this case, thermal information, which SI wave takes into account for various electronic parameters. Another level up, we're kind of at the assembly level. So you see we have some packages here, or the system level. You might think also motors and various things with propellers. So IcePak also integrates with mechanical for these types of simulations. Integrates with HFSS as well for these types of things. And similarly, the thermal and electrical information is passed back and forth in order to get a good idea of how your simulation will perform. And again, these are more properties of mechanical. You can import basically any type of 3D file into these solvers. Okay, so that was all the scales that IcePak can operate on. Now we'll get into some of the features that were mentioned at the very beginning. One that was mentioned was the dynamic performance over time of a design. So this is important. You want to consider, for instance, the time it will take for the thermal energy from one phase to dissipate before simulating the next phase, right? Let's say you were just simulating independently, maybe a cell phone with browsing and GPS active, but you never had simulated it after a long call in which the phone had got hot. You may be underestimating the initial amount of heat that the phone was starting at. So this is very powerful, and it can be automated to a high degree. So network modeling. So this is what was kind of referenced by reduced order modeling here. So what this allows us to do is make a thermal resistor network which models various designs. So in these, the nodes would represent different portions of the design. And this would be constructed by simulating doing the actual CFD simulation in many different circumstances, and then constructing this simplified model from that point. So once you have this model, you can do very, very quick iterations, which do take into account heat. So maybe instead of exporting to IcePak and importing the results back, you every time, if you know you're going to be doing maybe, let's say, a long optimization of some of the electrical properties of a PCB, for instance, one could make this model, attach it in the electronic solver, and then solve very quickly while still having a realistic idea of what's going on thermally. And of course, these can be as arbitrarily complicated or as simple as you like. You can have a node for each different type of material in your design, or you could just have lump a few different types of materials in together and represent them as one node. You have a high level of control. So this was just reiterating. These are the specific solutions which IcePak integrates with. So for the chip level, we got Red Hawk. For assembly level and system level, we got Maxwell and HFSS, Q3D. PCB level, SI Wave. Again, system level would be mechanical. And Twin Builder for performing multi-physics analysis with many different solvers involved. And the last one, last but not least, is its integration with Sherlock, which we will go more into in a moment. So we will we'll have a little introduction to Sherlock, and then we'll show the integration between IcePak and Sherlock. So to sum up, for thermal reliability, it really does start with having a good picture of your nominal design variation. And you can really only do that without spending a ton of money with a good simulation. IcePak will import from a ton of our different electronics and mechanical solvers and give you a great picture of what's actually going to happen once you have that on the bench. So now a little bit more about Sherlock. So Sherlock is our reliability software. So this allows you to mitigate a variety of different situations which might cause your design to fail, not immediately, but over at that 5-year mark, that 10-year mark, etc. So it will take into account temperature, specific shocks, vibration, solder fatigue, like we had said earlier, and it also includes some design for manufacturing risks. So this might be portions of your design which aren't manufacturable. They might not have a very good yield. Think like traces that are on the very thinnest edge of what your PCB house can manufacture. Those aren't going to come out as good as, say, fatter ones. Just like IcePak, Sherlock can also be integrated with many other of our simulation tools. So this is one of the features of IcePak, one of the simulations, which I find to be the most useful and just really gives you a great idea of everything, a good like bird's eye view of everything that's going on as it pertains to reliability in your device. So what we have here is a time to failure prediction. So what we have is the likelihood that the design will fail at any time due to any specific cause. So as we go on, you can see how the probability of each rises in different ways and how they sum to create the overall risk of failure for a specific device. So this is really important for letting you know what should I focus on in the first place. This is kind of a general, doesn't really pertain to thermal reliability per se, but this is what would tell you, hey, my thermal cycling solder fatigue is causing most of my failures. That's what I should focus on. It's just a awesome feature of Sherlock rather. So here's some of its other capabilities. You can do in-circuit testing, CAF failure, conductive anodic filament failure. So this is like this is kind of similar to electromigration, but it's kind of an electrochemical effect that causes bridging of two conductors. Plated through-hole fatigue. It'll even model your semiconductors wearing down over time, and also do design failure mode and effect analysis. And the focus of our next couple of slides, it integrates very well with IcePak. So now we will show you a little design workflow here. So just summing up, Sherlock is our reliability physics tool. It has many different types of physics and it integrates with different solvers. It's focused on PCBs, so it's basically for anyone concerned with their PCB lifespan. It'll model temperature, reflow failures, mechanical effects, and it can give you that bird's eye view of the different failure modes of your device. Summing up IcePak, it will integrate with basically any of our electronics and a lot of our mechanical solvers to give you that good picture of how your design is going to perform with different temperatures. And the great thing is that they integrate together very well. So what we're going to get in today is specifically a solder joint fatigue that does take temperature into effect. So many of the different analyses will be affected by temperature, but for this instance, we're just going to show off a little workflow that shows how your solder joint fatigue might be affected and the details of how you will actually perform this simulation. So here is our general design flow. So we got our PCB in Sherlock, right? What we're going to do is export the geometry information and the material information to IcePak. This kind of has a nitty gritty, but it's kind of it's pretty simple. It's simple as a few button clicks. We're going to run that thermal analysis with all of our components in and our electrical information. And then once we have that good CFD produced picture of the thermal performance of our board, we're going to bring that back into Sherlock and see how the solder joint failure is affected by that temperature. So this is how one would export all of your electrical and component information into IcePak. So it's simple as just going in the project tree here and exporting an FEA model. Then you'll export as an IcePak file and choose the specific options which pertain to your simulation and click display the model after export and it will pop right up for you. Behind the scenes, what's happening is STL files for the different components are being produced. This is just a 3D geometry representation of each component. And then we have the TCL files, which shows our material properties for each and more metadata concerning the components. This kind of displays what I was just saying. What's going on with the TCL file? We can see name of the component, its material information. And what you're concerned about more is just seeing this pop up. So here we see a Sherlock export in IcePak. So what you see here is the all the different packages we got going on. We have some electrolytic capacitors and then some ICs here. And what you'll do is just take a look at this imported model, confirm the power dissipation on each terminal, etc. Then you're just going to set up your thermal simulation how you like and solve. This can mean many different things for you. So this could include a fan. This could be a have many different ambient temperature conditions. Basically, this is where you will determine like the operating conditions here. For this analysis, we did 2 different temperatures at the extreme ranges of the thermal cycling, which we intend to apply as part of the solder joint fatigue. There'll be more on that later. So once you do choose your thermal setup and simulate, you'll see something like this. So now we have a mapping of each point on your PCB and on the components to a specific temperature that's motivated by the power dissipation. Okay, so now the next step is to send that thermal information back into Sherlock. So there's 2 ways we can do that. We can either export just a mapping of each component to its max temperature, and then Sherlock will consider the entire component to be that temperature, or we could we can export the temperature as it varies throughout the PCB, which will capture this effect of, gradients throughout the device and throughout the PCB. So writing out the CSV is pretty easy. Once you'll just select all the components that you'd like to apply a temperature to. This means you can exclude certain components, all in the interest of speeding up your simulation. Choose a few options. You could, if you don't like having the maximum temperature per component, you don't have to do that. You can also do mean. Maximum would just gives you that little bit of margin, right? So the analysis would look worse than it actually would be, right? It's a hotter temperature than it actually would be. And then just export it to a CSV. The second option actually works by exporting a PNG. So what you'll do is just export the PNG from IcePak and then bring it into Sherlock. This is done by clicking in the design pane. So now that you've exported everything, we can start on performing the actual solder joint analysis. So as you might know already, solder joints, there's what's connecting your packages to your PCB and all of your different components to your PCB, and even sometimes providing mechanical connections. And the same way that we detailed at the beginning of the report, changes in that coefficient of thermal expansion cause the shear to be applied to the solder and cracks to form. And repeated thermal expansion can kind of cause those little fractures to wedge farther and farther until you get something catastrophic like an open circuit. many things impact the solder joint fatigue. It's influenced by the maximum temperature of the temperature cycle, minimum temperature, how long it's staying at each time, the average temperature, and your components and electrical properties of your PCB. So it's actually, behind the scenes, Sherlock is actually calculating the strain. It is doing a mechanical simulation using that thermal information. So that is the method by which it's figuring that out. So to set your solder joint fatigue analysis up, you will first put in your reliability goals. So let's say this might look like I only want 10% of my PCBs to fail after 7 years or 10 years or 5 years. All of your parts, which you'll already have present, the mechanical properties, which will be present. It's just good to double check before you perform the analysis. And then lastly, we'll export these, we'll import this thermal information that we had just exported for IcePak to get that good thermal information. So we're gonna do a few different design variations, the thermal map, as previously mentioned, and the image, as previously mentioned, the map being the map between the components and the different temperatures. We're gonna assume 10 degrees Celsius and 65 degrees Celsius as the temperatures for the board and components. So you can see how this is varying. And this is this would be a daily cycle, right? So this is varying from 10 degrees Celsius up to 60. So you take in your CSV information pretty easily. You just go to drag it right into this files tree, and then you can add the thermal, you can say it's being affected by that thermal cycle, which we detailed here by going to edit properties and then pointing to that. So once the simulation is complete, you will see the maximum and minimum temperatures scaled by the electrical performance of the board, which had been simulated in IcePak. Another way you can do that is dragging in that PNG and then pointing towards the temperature cycle. To clarify, we are having 2 different IcePak simulations for each here, and you're saying this temperature map corresponds to one section of the temperature cycle and one to the other. So you could expand this as much as you like. You could have like 3 different temperatures if you like, et cetera, et cetera. And it will interpolate properly between the 2 or between as many as you like. So similarly, we're gonna do the same thing, associate this 10 degrees Celsius temperature contour with the corresponding portion of the cycle in Sherlock, and same thing with 65 degrees Celsius. You do have to scale the PNG to the extents of the board, which is pretty simple. And then Sherlock knows about this mapping of temperature for each of those 2 ambient temperatures, which is taking those electrical effects into account with the extant conduction and convection as well. So now we can set some more material properties of our solder joint fatigue analysis. So you have to, one thing that's good to do is confirm which type of solder you're using, as that of course affects how quickly it gets fatigued. And here we have the results. So from left to right, we have the map on the left showing the failure rate given the mapping of components to just one maximum temperature from IcePak. We have the thermal image, which is showing the gradient across the components and the PCB. And we have the just ambient temperature Sherlock simulation, which doesn't take into account the electrical performance, so like that heat caused by dissipating current. So as you can see, the thermal map is failing first at 2.9 years, hitting 20% of designs failing at 2.9 years. Happens for the thermal image simulation at 3.2 years, and happens with no input at 4.9 years. So this lets you know what kind of information you're getting. If you're not taking into account those electrical properties, your designs are going to fail a lot sooner than you had taken them into account, of course. But you can also make sure you dial in the amount of fidelity your simulation has. So for instance, if we had just used the maximum, things are going to fail a little bit earlier, and this is intuitive because instead of just like the gradient over those chips being present and us having those lower temperatures at certain part of the chips, in those simulations, those parts which were a lower temperature are now a higher temperature. So of course, more temperature gradient, more thermal expansion, more failure. So you can use this to really dial in when your devices will fail and plan accordingly.